power outages. Whether caused by storm damage or just a tripped circuit breaker, it's always problematic when the lights go out. Hi, I'm HDIAC subject matter expert Joel Hewett, here to discuss how new analytical and simulation technologies can help our nation's electric grid resist interruptions in service, and to bounce back quicker when outages do occur. This characteristic is known as resilience. The concept of resilience has been used by ecologists for decades, but only recently has it come into widespread use by experts versed in critical infrastructure protection. When faced with a major disruption like a storm, a resilient electrical generation, transmission, and distribution system, or the grid for shorthand, absorbs its effects, adapts to new circumstances, and swiftly recovers from the event. For more than a decade now, both federal agencies and the DoD have pointed to insufficient resilience in the grid as a major threat to homeland defense and military readiness. In 2008, the Defense Science Board warned in its More Fight, Less Fuel report that, quote, almost complete dependence of military installations on a fragile and vulnerable power grid places critical military and homeland defense missions at an unacceptably high risk of extended disruption, end quote. Soon thereafter, DoD began to use the term power resilience when discussing the risks posed by a fragile electrical grid to mission assurance. Since that time, many stateside DoD installations have taken successful steps to mitigate vulnerabilities by switching to microgrid operations, adding distributed generation sources like photovoltaic panels, and installing on-site energy storage systems. However, as DoD's Installation Energy Testbed noted in January of 2018, major commercial power outages are actually on the rise, and this is a trend that affects nearly every critical military and law enforcement facility from coast to coast. Helping us navigate the concept of grid resilience further and the technologies behind it is Dr. Fangxing Li. He's an engineering expert and professor at the University of Tennessee, Knoxville.
My name is Fangxing Li. I'm the James McConnell Professor at the Department of Electrical Engineering and Computer Science at UT. My research interests include power system economics, renewable energy integration, and demand response. Power system resiliency is a relatively new concept, which means the capability for a power grid to return to its normal service after a disruptive event. So it is, in plain language, the power grid resiliency means the ability to keep lights on under disruptive events like an earthquake, a hurricane, or a cyber attack.
So just how capable is the power grid at keeping the lights on after a major disruptive event? The grid is fragile in large part because it's simply getting old. A large portion of the grid's distribution and transmission lines were first constructed as early as the 1950s. Additionally, the average functioning U.S. power transformer is over 40 years old, well beyond its intended lifespan. The series of high-voltage lines that transfer electricity over long distances are currently operating at nearly full capacity, leaving grid operators and utilities with little margin for error. One trend working in favor of grid resilience is the modest growth of electricity demand on a national level. Energy efficiency gains have mostly offset capacity added due to economic expansion. Annual growth rates in energy consumption have remained below 2%, and sometimes negative, for nearly the past 20 years. This has helped keep strain on the grid to a minimum. But the rising rate of power outages raises an important engineering question. In what ways does the concept of grid resilience differ from the older and far more common metric of grid reliability? Dr. Li explains.
Power grid resiliency is somewhat similar to a more traditional term power grid reliability. However, reliability is more or less about a low, a high probability and a low hazard event. Uh, Resiliency means capability to return to service under a disruptive event. So that's why it's relatively newer. Reliability has been measured with a lot of different reliability indices like system average interruption frequency index or system average interruption duration index. But for resiliency, because it's relatively new, so there's really no broadly accepted measure or index for resiliency. I know there are some ongoing research works at national labs and some research organizations targeting how to measure resiliency.
Dr. Li is right. Measurements of reliability like SAIDI have been formalized by industrial groups like the IEEE. However, whether you call it resilience or resiliency, no consensus yet exists on how to quantify it as an evaluative characteristic of infrastructure protection. Ongoing R&D efforts of the Department of Energy are seeking to do just that. Researchers at Sandia National Laboratories recently developed a prototype 7-step resilience analysis process built to aid engineers and utilities in crafting system-specific resilience metrics. DOE's Grid Modernization Laboratory Consortium has since expanded upon Sandia's foundational work, proposing resilience quantifiers that combine direct metrics like the cumulative tally of critical customer hours of outages, or the financial cost of repairing grid damages, with indirect metrics like qualifying which critical services lost power and how severely their operations were affected. In late 2017, a research group at PNNL published work that challenges the usefulness of such resilience metrics, contending that they overlap too closely with traditional reliability metrics that only reflect whether a utility is meeting customer demand for electricity. The PNNL team argues that proper grid resilience is the ability of the grid to, quote, withstand grid stress events without suffering operational compromise. In other words, some grid modernization experts hold that a truly resilient grid only has to bounce back from stressing or straining events, not disruptions severe enough that they cause an actual power outage. Either way, once fully developed, these resilience metrics will inform how regional utilities act to harden the grid and to enhance its flexibility in the face of stressors. In some regions, the simple act of burying power lines can greatly boost reliability. However, in other regions, doing so makes lines vulnerable to flooding. That being said, vegetation management is beneficial everywhere. Because it is so imperative to keep power flowing to critical services, like hospitals, DoD installations, or fire stations, one of the most promising solutions available is the expanded use of microgrids.
One thing we can do is to use microgrids to enhance the resiliency of power grid. A microgrid is a small, local, active power grid which include distributed generation, distributed energy storage, and load. It can operate on its own as island mode, especially under disruptive events. Or it can operate in parallel with the main grid. So then we can supply power to the load from the main grid under normal operating hours.
In collaboration with Sandia, DoD has recently broadened its interest in microgrids, piloting some of these systems at bases in Colorado and Hawaii. These projects sought to standardize the military's approach to the design, installation, and even contracting methods used in providing microgrid services to secure DoD installations. For example, at Redstone Arsenal in Alabama, the Army has added distributed generation connected to medium-term energy storage capacity. In other words, a large stationary battery. Redstone has not opted for a microgrid, although that is a possible next step. As Dr. Li explains, a microgrid, despite its name, is not just a smaller version of the electric grid.
The operation and control of microgrid is definitely different from the operation and control of the main grid. The reason is that we should have a lot of distributed energy resource or demand response or energy storage in a microgrid. And many times they are inverter based with very little inertia, what we call inertia. So the control will be different. It needs better communication, control, and computation.
Integrating a series of microgrids into the national system will alter how it responds to disruptions. Because most power outages propagate from the distribution sector of the grid, any R&D that informs how the full system will react to a stressor, whether a storm or a tripped breaker, is uniquely beneficial to the aim of engineering resilience into the grid. And that is what Dr. Li's group does at UT. The Center for Ultra-Wide Area Resilient Electric Energy Transmission Networks, known as CURRENT, is a National Science Foundation and DOE-funded group seeking to engineer a nationwide transmission grid improved in both reliability and resilience. Established in 2011, CURRENT in part looks to facilitate the integration of off-cycle renewable and other distributed sources into grid operations. The CURRENT team, which also includes researchers at Northeastern University, Rensselaer Polytechnic Institute, and Tuskegee University, has built two distinctive modeling and simulation facilities at UT that together cover more than 16,000 square feet of space. The first is known as the Hardware Testbed. The Hardware Testbed is unique among grid modeling and simulation technologies for its lessened dependency on assumption-based algorithms. The Hardware Testbed gathers data from power measurement units, frequency disturbance recorders, and other supervisory control sensors attached to the physical emulators.
At Current, we implemented a hardware testbed and a software-based large-scale testbed to better model the power grid and improve the resiliency of the grid. Our hardware testbed is a testbed based on hardware, or we use circuit components like resistors, reactors, and power electronic components to build a miniature of a power grid so we can capture the response under disturbance. Also, we can propose controls and implement in this testbed to see how well our control algorithms can improve the system's reliability or resiliency.
As a physical model of a transmission network, the hardware testbed directly emulates how large-scale power systems handle changes in load, DC transmission rates, the addition of renewable sources like wind, solar, or hydro, or the addition of energy storage. This allows grid engineers to identify scenarios that may lead to voltage instability or voltage collapse. Current also operates what it calls a large-scale testbed, or LTB, which is built to mimic the communication and control functions of a wide-area electric grid. As a cyber-physical system, the LTB allows current operators to simulate the grid's physical, energy management, and communication systems in conjunction with innovative wide-area measurement-based controls. Use of the large-scale testbed provides critical insight into how new technologies will alter the operation of future power grids. It also allows researchers to identify areas for additional R&D. Dr. Li elaborates.
At Current, we also developed a software-based large-scale testbed to perform real-time simulation of a power grid under small or large disturbance. And we target to model a power grid at the scale of tens of thousands of components. In the hardware testbed, we use the actual physical components to mimic a power grid. So it is difficult to develop a hardware testbed to model hundreds of components. So we usually use it to verify a concept, to verify a new concept or a new algorithm. Usually we use the hardware testbed to verify a new control or new algorithm to improve power grid performance at the scale of tens of components. Once that's verified, we can move that concept to a large-scale testbed to try it in a much larger power grid, such as containing tens of thousands of components. So the new control or new algorithm is the outcome of the research. It can be a new actuation system or a new control algorithm.
In 2017, the National Academies of Sciences, Engineering, and Medicine conducted a major review of the role that resilience plays in protecting the critical infrastructure of the electric grid. In their report, they called for advancements in what they termed a visioning process, or the systematic imaging and assessment of plausible, quote, large area, long duration grid disruptions that could have major economic, social, and other adverse consequences. Current's large-scale testbed allows engineers to assess potential disruptions to the grid in just such a fashion. In the following clip, Dr. Li explains how the visualization room at Current aids his work on frequency damping control.
Here is a quick demo to illustrate the capability of the Current Large-Scale Testbed, or LTB. As this video shows, the left side is a non-controlled case, while the right side shows a controlled case for power system wide area operation with high penetration wind power. As you can see, the oscillation is damped a lot quicker in the controlled case. This study shows that the LTB platform can really demonstrate the advantage of new algorithm or control for power grid operation. So researchers can develop their own measurement-based new algorithm and then plug it in the current LTB for easy validation and verification. For instance, without the front-end visualization, it's extremely difficult to find out what's going wrong in the enormously large volume of data at thousands of nodes with the data rate like 20 snapshots per second.
As Dr. Li sees it, microgrids represent the best path to enhancing the resilience of the national power grid. And as we've seen, utility customers and warfighters alike will benefit from innovative efforts that seek to improve the base reliability of the grid, while also contributing to its resilience. Thanks for watching. Visit us at HDIAC.org and follow us on social media.